Welcome to the new lesson. Today we will study DFS with adjacency list. In our previous lesson, we studied BFS with adjacency list. In general, you should remember two main key points which are different with BFS and DFS. With BFS, you explore the graph level by level. For example, when you start from number 1, then you start next level 2 and 5, and then next level 3 and 4, and then next level number 6. But with DFS, you start from one side and go as deep as possible. For example, you process number 1, you process number 5, you process number 4, you process number 6 as deep as possible. Then you backtrack. It was the first important, how it explores the graph. The second point, in order to implement a level by level exploration with BFS, we use a queue data structure. However, with DFS, in order to implement a deep first search traversal, we use a stack. So let's practice DFS with the same example and find out all the similarities and differences. Okay, so here I have the BFS with the same example. The graph is already represented here using an object. So now let's create our DFS function. Const DFS equals so we pass the starting point that from where we start traversing our graph, and first we create a stack, const stack. With the BFS, you created queue first. For example, here the codes for BFS is also available. You can compare them. I think it's a good lesson for you as well. So create your stack equals and directly add the starting node in the stack. Start, that means add, let's suppose we start processing from number 1, so add number 1 to the stack. Okay, number 1 added to the stack. And also we need to create a set in order to keep track of the visited nodes in order to avoid the repetition. Okay, const visited equals new set. So, and whenever you visited a node and process that, then you add that node into the visited list. So you start processing your stack as far as that is not empty. So you say while stack is not empty, stack.length is greater than 0. Every time get the last inserted node, const current equals stack.pop. It removes or it extracts the last inserted node. Right now, number 1 is the last inserted node. With this one, we remove this from the stack. So now we check, is this node already visited or not? So we say if it is not in the visited list, so let's add this into the visited list. If current, if the visited dot has current is negative, that means if it does not have the current node, so add this to the visited set. Visited dot add current. So when we say add current, that means we add number 1 here. Number 1 added to the visited list. Okay, and now when we visited number 1 in the graph, this node, so we have to get its neighbors and processing and start adding its neighbors into the stack. So first in this structure you see that the neighbors of number 1 is a list, an array. So first get this array from this object, and it's already a very easy thing. So let neighbors equals adjacent, we are getting the neighbors from this object, adjacent list. The key is we are passing the key, which is number 1 right now, or that extracted node, which is stored in current. Okay, so this we got this array, which is the neighbor or adjacent node for this node number 1. So now we have to loop through this array and add each of them in the stack. However, here you should remember one point. In order to keep an order, you start adding the neighbors from the last neighbor in the stack. So say for let I equals neighbors.length minus 1 as far as I is greater than or equal to 0, I minus. Okay, so every time you need to get a specific neighbor. For example, let neighbor equals from these neighbors I. At this point you received this number 5 because neighbors.length is 2. 2 minus 1 means 1, and when you pass number 1 to this array, that is 5. So you got number 5. And now before adding number 5 to the stack, check if it is already visited or not. If it is already visited, so you don't need to repeatedly add that. So check this if it is already in the visited list or not. If it is not in the visited list, the neighbor, then add this to the stack. Stack dot push neighbor. So number 5, is it in the visited list? No, it is not. So let's add this to the stack. Number 5, add it to the stack. And then this loop continues because this array have 2 elements. So next time when the iterator becomes minus, it is 0. So at this point we get let neighbor 0. That means we get this node 2. Again we say, is this node number 2 already in the visited list? No, it is not. So add this node also to the stack. So now let's add number 2 also to the stack. Okay, and now the neighbors finishes because there were only 2, and now the iterator is 0. So again at this time when we check, is q.length greater than 0? Yes, the q now has 2 value. So again, so we get the last inserted node, which is number 2. Now let's remove number 2, and when we remove number 2, we check, is this added to the visited list or not? So number 2 is not added to the visited list, so we add that here. Number 2 is also added to the visited list now. So now let's check the neighbors of number 2. So here we get the neighbors of number 2. The neighbors of number 2 is 1, 3, 5. So we also start searching from the last node, which for example here that is number 5. Is number 5 already in the visited list? No, it is not. So we add number 5 again to the queue. So now let's add number 5 again to the queue. It happens that you add repeatedly in the queue, but you, when it comes to process, you do not process this repeatedly. Don't worry about this. Okay, and again, when you check number 3, is number 3 already added in the visited list? No. So add this also to the stack. Add number 3 also to the stack. Okay, and then we check the number 1. Is number 1 already added in the visited list? Yes. So we do not add this to the stack. And then the stack continues. It says, is the length greater than 0? Yes. So remove the last inserted node, which is number 3. Remove this. And now get its neighbors. The neighbors of number 3 is 2 and 4. So start checking from the last one, which is number 4. Is number 4 already added in the visited list? No, it is not. Oh, one mistake here. When we removed number 3, we did not add this here. Let's add that here, number 3. Okay, and now number 4. Is number 4 already visited in the visited list? No, so let's add this to the stack. Okay, and how about number 2? It is already in the visited list, so we do not add that to the stack. And the loop continues. This one length is 3, so we remove the last inserted node, which is number 4. And when we remove, we check, is it already added to the visited list? No, so add this to the visited list, number 4. Okay, and now get its neighbors. The neighbor of number 4 is 3, 5, 6, and start processing from the last one, which is number 6. Is number 6 in the visited list? No, so add the number 6 in the stack. And the second one is number 5. Is number 5 in the visited list? No, so add number 5 also to the stack. And now come to number 3. Is number 3 already visited? Yes, number 3 is already visited, and we do not add this to the stack, and the loop continues. At this time, stack.length is 4, so we remove the last inserted node, which is number 5. Okay, number 5 is removed, and then we check, is number 5 added to the visited list? No, it is not. So add this to the number 5. Number 5. Okay, add number 5 to the visited list, and now get the neighbor of number 5, which is 1, 2, 4, and start checking from the last one, which is number 4. So is number 4 already visited? Yes, so do not add this. How about number 2? Is it already visited? Yes, so do not add this. How about number 1? Is already visited? Yes, so do not add this. And the 4 ends. So at this time, stack.length is 3. So remove the last inserted one, which is number 6. Remove this and check, is it already visited? No, so add this to the visited list, number 6. Oh, what happened to that? Okay, we added number 6 to the visited list, and now get the neighbor of number 6. Neighbor of number 6 is only 4. So here check number 4. Is number 4 already in the visited list? Yes. So do not add this to the stack again. So again check stack, the length is greater than 0, which is 2. Remove the last inserted one, which is number 5. Is it already added? Yes. So we do not add that again. So when we get the neighbors of number 5, they are already processed. So again, when it comes to the last check, the length is greater than 0, so we remove this and we check here. Is it already added? Yes. And when we get its neighbors also, they are all already checked, and we do not need to add them to the stack again.